The total gravitational torque which is acting on a body is 0. So here it is providing a vertical upward force which is said to be a reaction which is opposite to the total weight of the particles present in this rigid body is lying on the axis. So this is the axis of rotation. Here whichever particle is there, it will have a 0 position vector. Hello everyone, I'm Brinda, Faculty of Physics from Vidhyaashram Pre-University College, welcoming you all to the session 4 of chapter 7, that is System of Particles and Rotational Motion. So in today's session, let us discuss regarding the equilibrium, mechanical equilibrium as well as principle of moment of lever. So here, let us discuss something about the equilibrium of a particle. So when can you say that the particle is in equilibrium? When two forces which is acting on a body are equal, then you can say that the particles are in equilibrium. That is, there is no force that can cancel each other. Both the sides also, the particle possess the equal terms and conditions, because of which you can just tell that the particle is in equilibrium. So here, if the particle is at the state of rest, where an internal energy or the external motion of the body doesn't change. There is no internal energy or an external motion for a body and for a particle which is present in the body, because of which you can say that the particle or a particle within an object is at the state of rest. That state of rest is a condition termed as the equilibrium of a rigid body. There is no internal reactions or the external reactions which is taking place within the body, because of which you can say that the rigid body is in equilibrium position, or else the internal as well as the external conditions, that is, it cancels out each other. That is, the terms which occur within the rigid body that cancels out each other. When it cancels out each other, you can say that it is in a constant motion. Then you can say that it is in equilibrium. So the state of rest of a body where neither an internal energy nor an external motion of the body changes with respect to time is known as equilibrium of the rigid body. So here, if the net external force and the torque acting on a body about the center of mass or any other point is said to be 0. That is, the net external force, the force is the one which acts for linear momentum. It gives linear momentum for a translational motion. So here we talk about translational motion. And torque, the torque which acts on a body is used for rotational motion, which gives you the angular momentum. So when the body rotates, you have an angle, so it is called as a rotational motion. You get angular momentum. So force is applied to a translational motion, the one which moves in a straight path. So it is a translational motion. So translational motion, you have got your linear momentum. So that is about your equilibrium of the rigid body. So suppose you're considering the force of each and every particle in case of translational motion. So we have got the total force F is given by summing up of all the forces of the particles which comes under the translational motion. So I tends from 1 to n. So this can be the force which is used for the translational motion of each and every particles present in the rigid body. And if you're having tau, it is a total torque which is representing the torque of each and every particle which is present in a rigid body which is undergoing a rotational motion. So this is like I is equal to 1 to n. This is the equation of torque. So when can you say that the object or the rigid body is in equilibrium? When the force or a torque tends to 0. When these two are 0, then you can say that the force is 0. That means there is no external force, no linear momentum. Again, there is no torque, no angular momentum. So that you can say that the object is in equilibrium, that is, it remains at the stationary point or it remains at rest or a constant. So this is all about the equilibrium of rigid body. Now let us go to the principle of moment of lever. So here we are checking about the principle of moment of lever. So here, what is this lever? Okay, so here lever means it is the one wherein a object, that is a rod, this is a bar or it is said to be a rod which is pivoted at the center by fulcrum, and here we are having two arms which is at a distance of d. Here also it is d distance, so I can term it as d1 as well as d2 distance, and we are having a reaction which is taking place over here. So that reaction is given as R, which is acting opposite to the direction of force. Here it is F2 and here it is F1. The force is acting downwards, wherein here you are calling it as load arm since the load is present, and here we give it as effort arm since we are exerting effort on this arm. So I hope you're clear with lever. So what is meant by lever? It is a thin rod which is pivoted at the center. Let the center be named as C and the rod is A as well as B, and the reaction is acting upwards, that is opposite to the direction of the force which is acting downwards, and there is a couple which acts. That couple is this arrow mark, the arrow mark which is represented over here, opposite arrow marks, that is termed as coupled, that is the force which is acting in opposite direction just to uplift this load. Okay, so here the two equal forces acting in the opposite direction which is applied to the uniform lever at equal distance. The distance d1 is equal to the distance d2. So at equal distance from this point is said to be the fulcrum. Counteract each other, that is, it cancels out each other, counteract each other, and it establishes a state of equilibrium. I told you, for the state of equilibrium, either no force should act upon or else the force should cancel out each other. So here there is a counteracting of each other, because of which the object is at the state of rest, or it is said to be a balanced one. So there is a balance in the lever. So this is the statement for the principle of moment of lever. So what does this principle of moment of lever tells you? That is, the two equal forces which is acting in opposite direction is applied to a uniform lever at equal distance. This is D1 as well as D2 by the fulcrum. It counteracts each other. It cancels out each other and establishes a state of equilibrium or a balance in the lever. So now here consider a light rod AB. This is A as well as B. The pink color rod, that is said to be a light rod. The two parallel forces are acting at the ends of A and B. So these two are the parallel forces. When it is in equilibrium, it acts downwards. So here in this case, it is one is upwards and one is downwards. But in the case of equilibrium position, when your lever is in this position, here it is your load arm. So it is F1 and F2 acting parallelly downwards. And let C be the midpoint in which the reaction R is acting upon in the opposite direction of that of the force which is applied, opposite to the force which is applied. So here, having this as a picture, now let us take up the derivation for the principle of moment of lever. So here we have got by translational motion. By translational motion, we have got R minus F1 minus F2 is equal to 0. This is R is equal to sum of two forces, which the two forces are got here. So it is R minus F1 minus F2 is equal to 0. So it is R is equal to F1 plus F2, which is got in this form. Now, by rotational motion, during the rotational motion, we have the equation as you have to take moments on the both the sides. So it will be F1 D1 and F2 D2. So again, let me draw a lever over here. This is the fulcrum pivoted at the center of A as well as B. So this is considered to be D1 and this is considered to be D2. Here you have got the center C where the reaction is occurring opposite to the direction of the force, that is F1 and F2. Okay. So here when we have this diagram, you can just look into it. So the force here, it is acting anti-clockwise. Here it is clockwise. Okay. So during the rotational motion, anti-clockwise you're considering it as positive, whereas clockwise will be negative. So while giving the moments, you can just take this arm, that is, it is known as load arm, and the other side it is called as effort arm. So this point is said to be effort arm, this point is said to be the load arm. So consider the load arm side. Since it is anti-clockwise, we are considering the positive F1, D1 and negative because it is clockwise. So F2 and D2, which is said to be 0, which can be equated as F1 D1 is equal to F2 D2, and furthermore it can be given as F1 F2 is equal to D2 by D1. So this is termed as mechanical advantage of the lever, mechanical advantage equation. Now by looking at this, you can just tell when the effort produced, when the force which is applied in the effort arm is said to be more than the force which is present in the load arm. So you can just tell that in the effort arm, when D2 is larger than in case of load arm, you can say that the mechanical advantage will be greater than 1. Okay, so that's all about your principle of moment of lever. Next, we are going to center of gravity. So here we have got center of gravity of the body. It is defined as point where the total gravitational torque acting on a body is 0. So the total gravitational torque which is acting on a body is 0. That means I'll just explain you regarding these things. Example, you can just take it as balancing the notebook at the tip of the finger. So here we have the center of axis. So here the balancing notebook at the tip of the finger, wherein this position is an equilibrium position, wherein the force as well as the torque both are said to be 0 or it cancels out each other. Here in this point it is said to be in equilibrium position because of which it is balancing. Okay. Now here the center of gravity means the point where the gravitational torque is said to be 0. That means the center of gravity means it is a place where the whole mass is concentrated at the center. Okay, so that the object is balanced. So now let us see, consider an irregular shaped cardboard box. Okay, so here we are considering the irregular shape, wherein this shape is irregular. Here I have given the regular shaped one. So if you're considering the irregular shaped cardboard and a narrow tipped object like a pencil, suppose if this is a pencil which is having a narrow tip over here. Okay, by trial and error method, you will have to locate, if you're having a cardboard of irregular shape or a regular shape, keeping a pencil, you just, by trial and error method, you just try in different points and see to that where exactly the cardboard gets balanced. So that is the method used over here. So we locate the G at a point on the cardboard. That is what I have explained you now. This point of balance is known as center of gravity, which is also termed as CG. CG in short, that is center of gravity. The tip of the pencil provides you the vertical upward force. So here it is providing a vertical upward force which is said to be a reaction which is opposite to the total weight of the particles present in this rigid body. So total weight of the particles given by m into g. For a change, I can give it as capital letter M into small letter g. So mass into gravitation, which depicts the total weight of the particles, which is given downwards opposite to that of a reaction, as we studied in the moment of lever earlier. So now the torque acting on a cardboard can be given as, the particles on the cardboard of each particle can be given as, this is by particle P1, this is the one what we get, and by particle P2, this is the term what we get. So summing up of the forces of the particles present in the cardboard, we have got summation mi, and g is the acceleration due to gravity. For each and every particle it is the same. So I tends from 1 to n, wherein this depicts the force of every particles which is present in the cardboard. And suppose if we consider the torque, suppose we are considering a torque, tau is equal to Ri, that is the ith particle, all the particles which is present over here, and F, which is a vector quantity Fi. So what do we have? So tau I is equal to Ri into Mi into G, because force is nothing but mass into acceleration, and since it is a downward action of a particle, that is a downward force of a particle, here you can say that acceleration due to gravity is acting upon. So now we can just give the total gravitational torque, which is given as summing up of tau I is equal to summation Ri into Mi into G, which can be termed as 0. That is because here when we have an axis and here there is a spreading up of a horizontal irregular shaped box, the particle which remains at the axis is having the torque of 0, because the r, that is the position vector for the particle which is lying, will be 0, lying on the axis. So this is the axis of rotation. Here whichever particle is there, it will have a 0 position vector. For rest of the other particles, the position vector ranges from r1, r2, etc. But the particles which is present in the axis will be having a position vector of 0. But the acceleration due to gravity, it has also got a force, but the position vector is 0. When there is no position, so when the particle which is present in the axis, it will have a 0 gravitational torque. So that is all about your center of gravity, because of which any particles which is acting at the center of gravity will be having a 0 gravitational torque. So in today's class, we have studied regarding the mechanical equilibrium as well as the principle of moment of lever and what is meant by couple as well as the center of gravity. That's all for today. Have a good day until we meet in the next session. Thank you.